Yeah, yeah, nice. Hello? Yeah, I suggest that we start without the organizers, but that's okay. Let's try to dig a bit deeper into the structure of these tensor networks today and be a little bit more technical. So these matrix product states. Let's first start with matrix product states, the one-dimensional case, and then later go to the higher dimensional analogs. But in some sense, the philosophy of all these systems are very similar, whether you do it in 1D or in 2D, or actually even in the continuum. The philosophy of all these methods is very similar, and also the way you actually deal with them, the way you optimize these tensor networks, the way you you calculate things. So let's try to see whether. So one beautiful feature of these tensor networks is that you can actually extract or calculate any expectation value. Okay, this is kind of course, this is why it's so useful, these tensor networks. If you would have a variational method and you can optimize your wave functions, but you cannot extract any properties of these wave functions, well, that's not very useful. And this is actually, you have to contrast this a little bit to, for example, the beta ansatz. Indeed, in the beta ansatz, you can calculate energies, but you can only calculate very few observables. It's apparently very hard, people tell me, to calculate correlation functions and all this, even if it's integrable, even even if you have the exact kind of representation of these wave functions in terms of the beta ansatz, that does not mean that you can extract all the relevant information. Well, this is really this can be contrasted to the case of these matrix product states, where you can actually calculate any correlation function. And I would like to kind of start with giving you some idea how to deal with this. So these matrix product states, so we introduced them in terms of these entangled states and so further, but this was more kind of the motivation. Okay, this was more to try to understand why why is this a reasonable thing to do? Why are these matrix product states kind of a good representation, or do they make sense from the point of view of ground states? So, but actually, from the point of view of computational physics, and we already wrote this down. The useful representation is that we would. So actually, let's consider actually the case of a finite chain with open boundary conditions. So I have like a finite spin chain, and I will kind of write it like this with open boundary conditions. And actually, it can also be. It is actually possible to take the uniform limit to the end to the thermodynamic limit. So you can actually really deal with infinite systems. But for notation-wise, I will also consider something that has periodic boundary conditions, but all these things at the end you will see don't matter. Of course, if you take a system with periodic boundary conditions into the thermodynamic limit, this is actually very similar to whether you have open or periodic. It will not matter for the bulk degrees of freedom. Okay, so what are these matrix product states? So I have n spins, and the wave function, like people in quantum chemistry, people call this the wave function. This is psi I1, I2, In. It's basically a tensor of with n indices, so therefore it has exponentially many values. But the whole point of matrix product states is that you make an ansatz for this kind of wave function, such that there's an efficient way of representing any of these possible coefficients. Namely, the coefficient corresponding to the value I1, I2 to In is given by the trace of matrix IA. So the AIs, so I and I runs from 1 to D, with D the dimension of your physical Hilbert space. So this I is not a power, it's really an index. Okay, so A1 would correspond to your physical state 1, A2 would correspond to your physical 2, and so further. And the amplitude, or the wave function, is basically given by the trace of the product of these matrices. Okay, so this is basically thus a matrix product state ansatz. Okay, and as we already saw, to actually use this now as a calculational tool, you want to have something like a normal form, or a canonical form. You want to bring this into a canonical form. It turns out that these AIs, if you kind of multiply, assume that they are all equal to each other. Okay, this is like a translation invariant case. If you multiply these AIs from the left with x and from the right with x minus 1, okay, so you do some kind of a gauge transform, we already discussed this, then this wave function doesn't change. Okay, because you see, you basically introduce an x minus 1 here and x there, they cancel and so forth. As long as x is full rank, this is a gauge transform. And actually the success of all matrix product state algorithms and the fact that actually they work so amazingly well has everything to do with the fact that there's really a very good choice that you can make for these gauges. There's like it makes sense to choose this gauge in a particular way that I will now explain. So if you have open boundary conditions, then you basically start here with a vector, let's call it 0, and at the end you end here with a vector 1. It doesn't really matter what this is, because we will actually consider systems that are in the thermodynamic limit. Yes?
But this trace with respect to what state is taken, or?
No, it's just a trace of these matrices. So this is the trace of a product of matrices. Okay. So these are matrices. Matrices, these are D by D matrices. And this is the product of these matrices, and then you take the trace.
Is the space associated with these matrices of some physical significance?
No, this is the virtual space. This is the entanglement space. Okay. So this actually has nothing to do with the physical space. Okay, this is basically this will, of course, this characterizes the number of variational parameters that you have if you want to deal with these kind of things. Okay, so let's try to understand basically how we can choose a good gauge. Okay, so like first of all, we would like to calculate the entanglement spectrum of this thing. Okay, so that means like we have this spin chain, and we would like to calculate these Schmidt values that we talked a lot about yesterday. So we would like to cut it, for example, here, and try to understand, okay, what are these eigenvalues? So that means that basically, to understand the Schmidt spectrum, or the singular, you want to take the singular value decomposition of that state, where these are basically the left vectors, and these are the left singular vectors, and these are the right eigenvectors. So this whole state can be written down as psi ij. We did this actually yesterday or the day before. This can be written down as ui I prime sigma I prime v j I prime bar. This is called the singular value decomposition. I guess all of you have heard of this. So of course you have to sum over the indices. So this basically any tensor with two indices can be decomposed as a unitary times a diagonal matrix times somehow another unitary. This is called the singular value decomposition. And so we're interested in, so these singular values are actually the square roots of the eigenvalues of your reduced density matrix. Okay, so how can you see this? If this is your state psi ij, then actually rho left would be equal to psi times psi dagger, when you interpret this as a matrix. And you see, this means that this is equal to u times sigma squared times u dagger, because this v will kind of pop out. And the rho right is equal to psi dagger psi, which is equal to v sigma squared v dagger. And that's of course immediately a proof that somehow the eigenvalues of the left reduced density matrix are equal to the ones of the right. But anyway, so what you're interested in is making sure that somehow this whole block here, so we'll now consider this block of spins with this one index open, that actually they form an orthonormal basis with respect to this index alpha. Okay, so this is a family of states, let's call them psi left alpha, labeled by that index alpha. And we would like this set to be orthonormal, such that basically they play the role of this U. Okay, so, and the same thing for the right-hand side, we would like to have that somehow everything to the right, which has the same index alpha, that this is actually psi right alpha. We also want that this is actually an orthonormal set. Okay, and then of course, we would have to kind of plug, so the whole state would then be basically this everything to the left. Then I would have something like the sigma that I have to put here, and then I have an orthonormal side for everything to the right. And then of course, if I can reproduce this, if I can make sure that the normal form of this thing is in this form, then I'm basically done. So how do you do this? Let's actually consider, so for this particular case, it's maybe easier to so how do you do this systematically? So you start basically from the left. Okay, so you we want actually, so I will have a recursive algorithm that will actually bring my thing into normal form. So I have this MPS. Okay, where the first matrix is actually this 0, well, I don't know exactly what it is. It's this 0 times AI. This is this block here. Okay, so this block, if I kind of erase this is this 0 AI, where this would be index I, and this is basically the 0 that you put on this here. So this is a vector. So that's, I can always make sure, well, of course, this is a vector, so actually for this index, it doesn't make sense that this index has a larger bond dimension than the physical dimension. Okay, this is a boundary effect. Okay, so I can just absorb that whole thing into the next tensor, and that's why somehow, if you kind of look at this MPS, all these first indices, somehow, as long as the physical dimension of these first indices is smaller than the bond dimension, I can just put basically nothing there. I can just put, I can reproduce this like this, like this, like this, like this. So let's assume that the bond dimension, that we are dealing with qubits. Okay, we are dealing with But so these things, it might look technical, but if you want to implement this, if you are interested in doing calculations with DMRG, if you're interested in calculating ground state energies, or like in these plots that I gave on the first day, these free energies, you have to deal with this. You have to kind of know this. So basically, what happens is that assume that the bond dimension is 8, and I have a system of qubits. Okay, then basically my MPS will only start after the 4th site. So the first 3 sites, I will basically have something like this, and now I have my first MPS tensor. Because this is 8-dimensional, I can just say, okay, this 8-dimensional spans my system of my 3 boundary qubits. Okay, and now I start kind of putting up my other kind of tensors here. Okay, and then at the end, of course, you would again put these 3 guys like this. Okay, so this would be somehow a way of writing the MPS, and you didn't do anything. This is still completely general, and this is now an 8x8 tensor. So this property that is psi left alpha forms an orthonormal set, from the point of view of contractions, basically means, so let's just ignore this, let's just plot this like this. Okay, so but you have this last index, you just interpret it as basically a system of the dimensions. Saying that this, if I would take this cut, and this is orthonormal, would be saying that this thing is basically the identity. Okay, I don't know whether this pictorial kind of thing is understood. So what it means is if I contract an index, I sum over it. So if this is the tensor A, this would basically be the tensor A bar. So it's just the elements-wise conjugation. Okay, because you have a bra and a cat. Okay, so you always have to deal with a wave function. Okay, this would be like psi, but somehow the things that I put on the downside would correspond to basically the bra. Okay, and this is, of course, if you have the bra and the cat, you have to kind of take a conjugation with respect to them. So saying that if I take this cut, everything to the left is orthonormal, forms an orthonormal set, kind of from the point of view of tensors means that if I contract this thing like this, I get the identity. Okay, so this kind of thing is basically just saying that there's no tensor sitting here, this is an identity. If this is an index alpha, then this index is also alpha. Okay, this is basically an identity tensor, an identity matrix. No, well, it would be an isometry. What it means here is that A is actually an isometry. Okay, that A, because it has like 2 indices to the left and 1 to the right, would mean that, so that A is like an isometry. It's kind of part of a unitary. It's like some columns of a unitary, and if you kind of conjugate them, then you get the identity. But it doesn't have to be unitary itself, just because, of course, the dimensions don't work out, because this is d-dimensional, this is also d-dimensional, this is also d-dimensional. So, sorry, this is small d-dimensional. So this has like, it's an isometry with small d times big D rows and d columns. That's what it says. But let's assume that this is not the identity. Okay, let's assume that this is basically a matrix row. Let's call it row. And why can I call it row? Or row 1? Well, because this is, of course, obviously a positive operator. Okay, because if you take this and look at this as a matrix, this is a matrix times its conjugate. And this is, of course, if you take a matrix and multiply it with its conjugate, this is always a positive definite operator. We call it row. But that means that, of course, this can be written as square root of row, square root of row. It's a positive operator, always has a square root. That means that if we now do a gauge transform, we basically say my first A, this A, I multiply it from the right with square root of row minus 1, so the square root of the inverse, this index. And this guy will have the property that's an isometry. So what I can do is basically put somehow this square root of row minus 1 here. But then, of course, I have to multiply this tensor with square root of row. Okay, and now you kind of go all the way to the left now. So now by putting this, I have done basically a gauge transform on this one tensor. And it's now an isometry. But now I also have to absorb this thing again on the next side. And now I do this recursively. Now I have the square root of row 1, basically, times A. Now I kind of put this thing, the conjugate, but this is a positive operator, so the square root is actually also the same. Then you have the A bar here. This will kind of give me now a row 2, which is again positive operator. So for the people that are familiar with completely positive maps, actually, if you look at this description, this is basically a tensor notation for a completely positive map acting on the state rho. Okay, because if you actually write this out, this effect of this is actually that this is the sum over I of AI dagger rho 1 times AI is equal to rho 2. That notation is equivalent to that notation. So this is actually the equation of a completely positive map. Okay, it maps a positive operator to a positive operator, and it's actually the most general type of matrix, most general map that does that. Okay, and this is actually very important, this interpretation in terms of completely positive maps, if you kind of start looking at the thermodynamic limit. Okay, so assume that actually all these A's are equal to each other, and you kind of keep on doing this procedure, no? So you see that we push basically this isometries through the kind of thing, and we keep on pushing this row. Whenever you have a completely positive map, then if it's a generic completely positive map, this has a unique fixed point. So this is very similar to a stochastic matrix. This is actually the quantum version of a stochastic matrix, a completely positive map. And the most important theorem concerning stochastic matrices is, of course, the Perron-Frobenius theorem. That tells you if I have a stochastic matrix and it's ergodic, then it has actually a unique fixed point, and this fixed point is strictly positive. So it has actually all the elements are strictly positive. And the quantum Frobenius the quantum Perron-Frobenius theorem is actually very similar. It tells you that if this map satisfies some conditions, and these conditions are the conditions of injectivity, then somehow this completely positive map will have a fixed point, and that fixed point is guaranteed to be a positive definite matrix, strictly positive definite. And that's basically the quantum analog of somehow the Perron-Frobenius theorem in stochastic matrices. Yes, there was a question? So completely positive map, I think, I'm not so sure that it was introduced in the other lectures, but this is the most, this is the equation of, this is basically the most general expression of a quantum channel. Okay, what is a quantum channel? It tells you I have a quantum system, and I couple it to an ancillary quantum system. I do some unity transformation on these guys. Okay, so I do some big unity transformation on these guys. Okay, this is like a rho, the system that you want, this is rho auxiliary. You take the tensor product, you do a big unity transformation on both of them together, and then you trace out the ancillary system. So this is actually, you have to think about this is like, I have a system that is interacting with the environment. They interact, and then the environment goes away. I cannot touch it anymore, so I have to trace it out. And I want to say, what is the evolution of the density matrix that I have? And that's exactly described by completely positive maps. Okay, yes, well, this is actually this is the constructive thing. So the completely positive maps are actually the unique set of all possible linear maps that you can do on a density matrix that preserve positivity, but not just positivity, it also has to preserve positivity if you kind of tensor your density matrix as positive with any other kind of, it has to also hold on if you do it on a part of a tensor product structure. And this is the mathematical definition. It's like the most general, it's like it has to preserve positivity for all possible density matrices. And the complete actually has to do with the fact it also has to preserve positivity if you're only acting on a subsystem with that map of a bigger system. And the typical examples, but these are all, the typical example of a positive map that is not completely positive is the transpose. I don't know if you've heard about it, but this is yeah, these are all techniques that are, it's not too important actually that you get this, but these are all kind of things that are very relevant in the context of quantum optics. Actually, what this was certainly introduced yesterday in the talk of Denis Bernard. So Denis actually talked about Lindblad equations. Well, the Lindblad equations are kind of, if you have dissipation, are nothing more than the continuous versions of that thing. This is the discrete version of somehow this Lindblad equation. So whenever you have noise or dissipation, you describe your quantum system like this. There was another question? Yes?
Yeah, that's what, so when you really extracted these, the positive map effectively, so this is the environment.
Yeah. So anyway, so what you have here is now you have the square root of rho 1 times A is rho 2. Well, you know what you do now. You kind of you bring this to the left-hand side, square root of rho 2 minus 1, square root of rho 2 minus 1, and so further, and this is now equal to the identity. You absorb this into the next one, and you repeat this. So that means that by doing such gauge transforms, I can, at the end, turn this matrix product state into something that I will draw like this. Okay, so this is actually the notation that all these kind of guys are now isometries in this direction. Okay, that means if I contract these two indices, I get the identity. If I contract this with its conjugate, I get the identity. So this MPS can now be written in this form. And so further. And I could, of course, have done the same thing from the right. I'm not very good in drawing these kind of things. Okay, so I do this, but of course, I'm still stuck now with these kind of guys here in the middle. Okay, so what will this kind of operator be in the middle? This will be like this square root of rho n times the square root of the row left n times the square root of the row right n. Okay, so this is the tensor that is sitting in the middle. But everything to the left is now an isometry, everything to the right is an isometry. So that means that actually the entanglement spectrum, all the eigenvalues or the eigenvalues of your reduced density matrix, these singular values, like we kind of did this, are nothing more than the singular values of this object. Okay, so to get the entanglement spectrum, what you have to do is take this object, square root of rho left n, square root of rho right n, multiply these two matrices, calculate the singular value decomposition of this, u sigma v dagger, and these sigmas are the singular values of somehow this wave function, and therefore the square roots of your eigenvalues of the reduced density matrices. So that means that all these Renyi entropies and so are nothing more than somehow the classical Renyi entropies of the squares of these kind of Schmidt numbers. There was a question? Well, this is just notation that this is an isometry in this direction. So it means that actually this thing is equal to the identity. But to contrast, basically, this is the left, and this is coming from the right.
Just to check that I see the picture of the drop test, so this was IK. Could you say what all of the indices there correspond to in the picture as well? So the I prime, and
Well, so a more fair thing would be that if I would have an alpha here, alpha, alpha, and alpha. And this I would be all these indices. And the J would be all these indices. And this would be the alpha. So this would be basically a 2 to the, whatever, number of indices to the left. This would be 2 to the n. But the thing is that, of course, these MPS give you an efficient description for these. You don't have to write out these 2 to the n indices. Okay, because you just look at this as a picture. This is basically what this psi left is. And what I did, so what we did here is nothing more than some kind of a gauge transform on this index that made this an orthonormal set. And then the inverse of that kind of thing is actually this, and this gives rise to the Schmidt numbers. Okay, so well, here, this is exactly how you do it actually in practice. No? This is how you would do it. This is how you would bring your MPS into canonical form. So it's a recursive procedure. No? Start from the left and kind of pull this thing to the middle. You come from the right, you kind of pull it to the middle, and that gives rise to these numbers. So in the translation invariant case, which is of course one of the more useful things if it's this completely translation invariant, then all these a's are equal, and then of course this. So the equation you have to solve is basically rho left times a bar is equal to lambda times rho left. Because of Perron-Frobenius, you're guaranteed that actually because this state has to be normalized, that this lambda is equal to 1. So the leading eigenvector of a stochastic matrix is always 1. And the kind of the quantum version is also, this is guaranteed that the leading eigenvector of that CP map is 1. So this is nothing more than an eigenvector problem for the matrix A bar. And this is actually called the transfer matrix. Okay, so this is like the transfer matrix of your thing. And you do the same thing from the right, and that's basically, once you found this row left and this row right, then basically you immediately have your Schmidt spectrum. The Schmidt spectrum is just, well, and this is of course independent of n, and it's really square root of row left times square root of row right, take the singular value decomposition of that. That gives you the full entanglement spectrum. Okay, so one thing that this picture immediately gives you is somehow the fact that all expectation values are decaying exponentially, that the correlation length of your system is actually finite. Okay, so why is this? So let's, for example, calculate the correlation function. Okay, so I have this MPS here. And I would like to calculate the correlation function between basically some operator here and some operator there. Okay, so you have to basically contract this tensor network. How do you do this? Well, you're saying, okay, this in principle is an exponential problem. But of course, if you kind of come from, assume that this is translation invariant. So contracting everything from the left, we'll put here row left. Okay, coming from the right, from infinity, so this is, you come from infinity here, you basically put here row right. Okay, because this is exactly, somehow if you take a matrix to a huge power, then of course it's just the leading eigenvector that remains. You have to, now this is a matrix, you have to multiply it with basically this matrix, and then you have to multiply it n times with somehow this transfer matrix. So if this is the transfer matrix, you have to take this to the power n. What we just saw, because of Perron-Frobenius, the leading eigenvalue of that matrix is 1. But of course, the second lead, the next eigenvalue, because this is a finite operator, will somehow be some number. Okay, so assume that the eigenvalues of this are 1, and then lambda, and all smaller ones. You immediately see that whenever you will calculate a correlation function, and you make sure that this is basically, you calculate the connected correlation function. So you take out basically the contribution from the row right. So basically you have to, the connected correlation function would be calculate this minus the expectation value of this times the expectation value of this. But the expectation value of this would mean basically put this row right to the right here. So this would be row left, O row right. This would be expectation value. So this is basically that out of this middle thing, you kind of erase that eigenvalue. You kind of erase that contribution. So that means immediately that if you calculate this expectation value, this will scale like lambda to the n. And therefore, the log of lambda is nothing more than the correlation length of your system, or the log of 1 over lambda. Okay, because this is, of course, equal to exponential of minus n times log. Is that true? 1 over lambda? Yes. That means that log 1 over lambda is the inverse correlation length of the system. Okay, and this is completely determined by the eigenvalue structure of your kind of transfer matrix. But this is, of course, nothing new. This is exactly what you get in statistical physics. If you look at the classical Ising model in 1D, and you calculate the correlation length, this is exactly how you do it. No? The classical Ising model is basically the one-line version of that. Classical Ising model is basically a product of matrices, like this. And if you calculate correlation function and everything in a 1D Ising model, well, you know that indeed everything decays exponentially, and somehow the full kind of structure is defined by the eigenstructure of the transfer matrix. So basically what we did here, what matrix product states do, is map the problem of a quantum problem to a classical problem in the same dimension. Okay, so that's exactly the dimensional reduction that is going on in the matrix product state kind of thing. So you start with a quantum system, you kind of come up with a wave function in a quantum system, and then calculating expectation values of your kind of in your state, or have the same complexity as calculating basically expectation values of a classical spin system in the same dimension. And of course, calculating expectation values in a classical spin system in 1D, think about the Ising model is trivial. This can immediately be done by the transfer matrix. And this is always, take any course of statistical mechanics. That's probably one of the first things you will do, is look at the Ising model in 1D. So this is the complexity now of calculating expectation values and anything else. Yes?
Please repeat this argument about the eigenvalues of I. So why did you turn this into a zero the first element? Or like...
Because I'm interested in the connected expectation value. So what is this? So this matrix, this one, is basically equal to rho right, rho left, plus lambda times other contributions. And if you calculate the connected correlation function, it would exactly somehow basically subtract that part. That is equivalent to that. Okay, so actually, let's indeed kind of because I'm going very slow. I thought, okay, whatever. But let's try to see what will happen in 2D. Okay, in 2D, I will have my Peps wave function, which is basically a standard network that looks like this. Okay, this is a much bigger. So this is, you have to kind of add an extra dimension now. So these things are the physical dimensions. These are the virtual ones. So how will we calculate expectation values for this? How will we deal with such a wave function? Okay, so we have to do this. We have to take the conjugate, so this is basically gluing something on top of it. And you will see that the complexity of calculating expectation values here will basically be equivalent to calculating expectation values of a 2D classical stat-mech model. Okay, because this is in some sense a partition function. It may be, you can interpret this as a partition function of a classical model. And it's exactly like this. This will be basically the partition function of a classical model in 2D. So how will you calculate expectation values in such a model? Well, this, of course, is very much like if this is translation invariant. Well, this is like, how will you, so it's clear what you need to have is these leading eigenvectors of the transfer matrix. And these leading eigenvectors of this thing are very similar now to calculating leading eigenvectors in the transfer matrix approach like Onsager did. Onsager had his Ising model. Calculating the leading eigenvector of the transfer matrix is exactly what he did. Well, we have to do this here. But we have seen, and yesterday we talked about this, that basically the problem of finding leading eigenvectors of transfer matrices is very similar to finding ground states of local quantum Hamiltonians. Okay, so here we also do the same thing. We start from a 2D quantum system. We come up with some ansatz in the form of a Peps. And calculating expectation values of this has the same complexity as calculating basically the partition function or the leading eigenvectors of a transfer matrix in a 2D system. This is effectively the complexity of calculating or simulating finding ground states of a quantum Hamiltonian in 1D. So we will use all these tricks that I will explain now to find basically these leading eigenvectors. And once you have those, we of course have everything. So what you see is that the way this works is by dimensional reduction. You have to solve a two-dimensional problem. You map the two-dimensional problem to 2D classical problem. You solve the 2D classical problem by basically mapping it to 1D quantum problem. And the 1D quantum problem you solve by actually mapping it to 1D classical problem. So there's this whole kind of quantum, somehow dimensional reduction in some sense, where all the features of your theory are kind of encoded into the lower dimensional analog. So for example, what you see here is that indeed this leading eigenvector of this kind of MPS encodes all the information. But you have to, of course, you must have both. You must have both from the left and from the right-hand side, but the two together contain all the information about the entanglement spectrum. Okay, so the transfer matrix, the eigenvalues of the transfer matrix completely control somehow the correlation function in your system. And immediately you already see that indeed 2 dimensions are much richer. Because in 2 dimensions, that's the big difference between 1 dimension. In 2 dimensions, you can actually have critical correlations, even for a classical system in 2D. And that's why, of course, these systems will be kind of much richer. Okay, so let's now actually take a step. Once we have this this formalism, let's actually try to do this this time-dependent variational principle that I talked about yesterday. Okay, so this time-dependent variational principle was about how do we actually find ground states now. Okay, so now I have kind of these canonical forms. How can I actually use this now to find the ground states or the matrix product states that have minimal energy, or the leading eigenvectors of my transfer matrix? That's exactly the same problem. So what you remember what we wrote down is something like AI delta over delta t times psi was equal to this projection on the tangent plane times h times psi. Okay, this was this picture. Now I had this manifold. I want to simulate a Schrödinger evolution, but somehow I'm taking myself a little bit outside of the manifold, so I have to project it back into the manifold. So I have to kind of put this projection on the tangent plane, and then I evolve. And this is the real-time evolution, and imaginary time evolution is basically putting a minus this. And if you evolve in imaginary time, you will actually eventually converge to the ground state. So you would like to kind of evolve your state in imaginary time on that manifold and evolve to the ground state of your kind of system, or the minimal energy, the one with the lowest. So what is this PT? So how do you actually construct a projection on the tangent plane? Okay, so we have this MPS. Let's assume that it's translation invariant. And this has all the same kind of A's. Okay, so the tangent plane, what is this? This is basically how does my wave function change if I do a small variation? Okay, so basically I have this wave function psi of A, and I want to take the derivative with respect to all these parameters, A, I, alpha, beta. Okay, so all these vectors, these will actually be non-normalized vectors because they are, of course, something like plane waves. No? Because if you take the derivative of a wave function with respect to a parameter, this will kind of take the derivative here, plus take the derivative there, plus there, plus there, plus there, and so further. So this will basically be something like a plane wave, but we don't really care about this. Okay, so this is, we understand, of course, the plane wave. So this, in some sense, these are not vectors in your Hilbert space, but they are directions. Nevertheless, these things span, we know exactly what the normalization is, you can perfectly deal with them. These span the tangent plane. Okay, so this is exactly the directions. So you're on your manifold. So you have your manifold. Okay, and you're in some point and you're interested, okay, let me kind of put the tangent plane on that point. And what are the directions in which can I move? Well, these are exactly all these directions. Okay, and so for people that know a little bit about differential geometry, because this is a Kähler manifold and all this, we know that there's actually always a choice. Okay, so of course we will have to make some coordinate choice. Okay, so we have a manifold, so we can make many coordinate choices, but there's always a coordinate choice that we can make such that locally somehow because this is basically a Riemannian manifold, an Euclidean manifold, such that locally it actually looks Euclidean. Locally, that's somehow basically the metric that all these objects are orthonormal. Okay, and that's very important. In practice, if you kind of want to have an efficient algorithm, you want to make sure that if you vary your parameters, you vary one parameter or you vary another parameter, that these correspond to orthogonal directions. Okay, this is very important for kind of having a well-conditioned algorithm. Okay, actually, the tricks that we did here to make these things orthonormal are exactly the same ones that we need to make this locally kind of Euclidean. So to make somehow your coordinate system locally flat. Okay, this is not very deep. So this is actually very, in some sense, all these things are not complicated. If once you write this down as an MPS, you will immediately see that indeed these transformations that I kind of talked about there are exactly the ones that will make somehow my geometry there locally flat. Okay, that somehow if I move somehow in some directions, well, all these directions correspond to orthogonal things. So that means that if this thing is basically, let's kind of write it as psi I alpha beta, this would be basically take the derivative of this MPS of A with respect to these indices, and you take here the conjugate I prime alpha prime beta prime, so this is delta I prime delta alpha prime delta beta prime. Okay, this is basically equivalent to saying, okay, locally I want to make this kind of flat. So what is this projector? So it can actually be very easily written down in terms of these operators or these kind of tensors that I wrote before. So you remember these were basically these tensors that I brought into canonical form, such that I made left orthonormal kind of guys out of it. Actually, I will kind of do this. And this is the conjugate. I have to connect. Sorry, I have to. That's the, so this projection on the tangent plane will be a sum over all my sides I, where this is basically the side I of this minus this thing. Okay, I will not kind of draw the arrows, but here all the arrows point to the right, here they all point to the left. Okay, so 1, 2, 3, 4, 5, and here I have 3. And this is basically the ith side here. Okay, so it turns out that this projection on the tangent plane has a very simple realization in terms of these tensors. It's just a sum of many terms, where somehow, so that means take any vector, okay, take any vector that you can imagine. For example, h times psi, okay, because that's what we want to do now. We had a state, we apply it a Hamiltonian, but this Hamiltonian can be completely non-local. This Hamiltonian can even be a transfer matrix. I don't care. Okay, this is exactly how you would do it for transfer matrix. So this is an operator acting on that state. And now I apply this projection on it, and I know that this thing will be living in this tangent plane. Okay, and it's you just can figure out that actually this projection on the tangent plane is exactly this operator. Okay, and it's an easy exercise to see that this is actually a projection. If you do it squared, it squares to itself, and all these kind of properties. And this, of course, is very important. You see that all these things are isometries. So that means that, of course, now we are basically done. Now we have our algorithm. Once you see that this is the projection, then somehow I want to. So it means take a state psi. Act with your Hamiltonian or your transfer matrix on it. It doesn't matter whether it has local or non-local, whatever operator is H. And now act with PT on it. This PT is just a sum of many terms. It's a sum of terms over I, where I is equal to 1, 2, it's basically all the sides. But you have to do this minus this. So you apply this big operator to it. For example, let's assume that we take this side. So it will have terms like this. Okay, so for example, this operator, this term of this PT acting on that state will be of that form. Okay, so this is this thing would be this thing is this, and that thing goes through. You immediately see that, of course, if I look at this state here, so everywhere to the left it looks like the original state. Okay, because the original state here was, of course, also written in this form. Okay, so I put this in canonical form, let's say that, such that these were all these kind of arrows pointing in this direction. And here I had my center, basically, and then everything here is kind of written in this direction. So what you have is that what comes out of applying this operator to this object is again something that looks exactly the same everywhere to the left of that object, looks exactly the same everything to the right, because these objects are equal to these objects. But this center kind of thing has changed. So basically what this tells you is the way you have to update that center side. Okay, so evolving now in imaginary or in real time, imaginary time or whatever, what you see is that, so this is basically the equation, no? d over dt times psi is equal to p, thus the projection times h times psi. So how do you solve differential equations that are sums of many terms? Well, you do the splitting method. You first evolve. So how do people solve, for example, Laplacians? They first kind of evolve with Laplacian, then with their potential, then again with the Laplacian and the potential. So this is, so you split now. So any practical way in which you solve differential equations, you always kind of do something like a Trotter decomposition. You evolve with some term of your Hamiltonian, then with another term, and so further. Well, what you see here is that I get an effective, and this is of course the symplectic equations, no? So what I was saying yesterday, that I get a classical effective system. Well, this is basically the description of that effective classical system that I will get. So I have to evolve this differential equation with respect to my tensors A. What it tells you is that I have kind of 2n, if I have n sides, I have 2n minus 1 terms, okay, because this actually runs from 1 to n here, but actually this only runs from 1 to n minus 1. So I have 2n minus 1 terms, and I have to evolve these 2n minus 1 terms in consequence. So first I evolve, for example, this term. What it says is that, what this means is that I only have to update this one side here. Okay, because if all the rest remains the same, the only thing that is not the same is this whole thing. So you have just to contract this whole thing, and this tells you how to change that middle side. Then I actually evolve with this thing. So this is exactly the same, but the only difference is that kind of I do this. So basically, this is now updating this center side. So you remember this row left, the square root of row left, square root of row right is this object. What this thing tells you is that you have to update that middle side. Then you again evolve with this one. Then you evolve this, and so forth. And this is exactly how all the algorithms that optimize matrix product states work. Whether it's DMRG, TDVP, TEBD, there's many different schemes that are around to optimize MPS, but at the end, they're all of that kind. So this is basically the union of all these methods. All these methods only differ in the ways you kind of do the splitting method. Okay, if you have a differential equation which is a sum of many terms, there's many ways of splitting that thing. You could, for example, if you have a translation invariant Hamiltonian, like a Heisenberg model, the typical way you would do your splitting methods, for example, you could first evolve with all the terms XX. And then with all the terms YY, because they all commute with each other, and then all the terms ZZ. Or you could evolve also only the even, so the even odd terms, and then the odd even terms. That's a different splitting. So all these different ways of solving somehow these differential equations is different, and exactly the same here. So once you reformulated your problem like this is kind of now giving you a general framework, and now you can choose what is the best splitting method for solving this. So what is DMRG? So DMRG was invented by Steve White in '92 and is really an extremely powerful method for kind of finding ground states of finite systems with open boundary conditions. So this DMRG is basically I take a system of n spins and I want to find the ground state. What is this in this language? It is actually the splitting method, okay, the splitting method in which you take delta t to infinity. Okay, so this looks like completely ridiculous, no? You would say, if I have a splitting method, I have to take delta t very small. Well, nevertheless, DMRG is really this splitting method where you take the time step going to infinity. And the reason why this is okay is because somehow you just always lower the ground, you always lower the energy by doing this. So basically what DMRG will do, if you take this time step to infinity, it basically tells you, keep all these tensors here fixed except the middle one. And now try to find the tensor in the middle that minimizes the energy of my whole system. And that coincides actually with this step. Okay, but and then you can basically sweep, you go from left to right, and you always minimize the energy, and so further. So that's basically how DMRG works. But of course, once you have this scheme here, if you understand it in terms of this manifold, this is basically automatic. Okay, so all these different methods are now kind of clear how to deal with this. So, in some sense, with this information, somehow this is more than enough to understand basically any paper that is written on DMRG. But this is not the typical way you will kind of see it explained. But there's a huge advantage of actually having this formulation in terms of these tangent planes. So let me kind of continue for a few more minutes before kind of stopping here. So, once you have all these vectors, okay, these delta over delta, ai, alpha, beta, psi, okay, these tangent planes. So these things, these objects define indeed the tangent plane on the state I have. So basically you evolve in imaginary time your wave function, you find the ground state, and actually this works amazingly well, no? So this gives you like machine precision basically for the ground state energies of very complicated quantum many-body systems. Or similarly, actually what this allows you to do is calculate the free energy of a classical stat-mech model. Okay, this is not obvious, no? So this, even for non-integral ones, with this method, you're able to find the free energy, the density of a classical stat-mech model, and therefore you can calculate entropies and everything you want. And this is very complicated to do with any other method like Monte Carlo. You cannot calculate it. So one of the cool things that we did last year is actually the two-dimensional, the three-dimensional version of that. We looked at a classical stat-mech model for ice. So really the ice the ice model that Pauling kind of envisioned, no? That you have like the pyrochlore lattice, and you're interested what is the ground state entropy, what is the zero temperature entropy of somehow ice. And people knew that there had to be some zero temperature entropy because there was some residual kind of, the people did experiments and they saw actually if they extrapolate somehow using the specific heat, somehow the entropy, that there's a zero entropy. And this is actually a combinatorial problem that you can formulate as a 3D stat-mech model. You want to calculate basically what is this entropy, and this is extremely challenging. People had never really been able to do this systematically using Monte Carlo, but using these methods actually we got kind of this entropy immediately. So this is something like you can calculate entropies using this, which is exactly the same problem as finding ground state energies. But of course these things do much more than just calculating energies. They give you the full kind of ground state wave function, and from this wave function you can kind of calculate any kind of expectation value. But now once you have this ground state, you can ask, okay, can I do more? Okay, because can I, for example, have access to more non-trivial kind of objects? Can I kind of have access to the to my dispersion relation? Okay, what is, for example, how does my kind of the energy of the excitations in my theory look like once I have kind of a ground state? Okay, it turns out that this effective to get here somehow a linear subspace spanned by these tangent vectors. And this linear subspace turns out to be exactly a very good kind of basis in which you can expand your elementary excitations. And why is this? Well, indeed, this derivative of your state psi, you saw this was like a sum of something happening here, plus something happening there, plus something happening there, and so further. Well, this looks exactly like a plane wave. And that's exactly true, and you can actually prove this using Lieb-Robinson techniques. So we used Lieb-Robinson techniques and so to justify this, and you can actually prove this, that indeed, if I have a system with a gap, then I'm guaranteed that my excitations are extremely well approximated by vectors in that tangent plane. Again, of course, this non-renormalizability of this is of course true, because the eigenstates corresponding to the lowest eigenvalues are typically plane waves, and these are the particles in your theory. And somehow now we can basically find them, because now what you do is we have this basis here, psi I alpha beta, which is an orthonormal basis. I can project now my Hamiltonian in that basis. This gives me an effective Hamiltonian in a very low dimensional space, and I can diagonalize that Hamiltonian. And then I can basically look at the energies that I get with this. And if you do this for something like the spin 1 Heisenberg model, and you do this actually, there's a slight modification because you want to introduce also some momentum. You are interested in basically the energy as a function of the momentum. So you have to kind of make sure that these derivatives are, that you make superpositions of these objects such that they have a definite momentum, but you can easily do that. And when you plot somehow basically the momentum, so you have something like a spin 1 Heisenberg model, and you plot somehow these energies as a function of momentum, or the lowest energies of these kind of objects as a function of momentum, you get some picture like this. Okay, so you get something that there's an isolated branch here, and then you get a continuum of excitations, and this is exactly what is called the Haldane gap. Okay, and all these objects here that live in this isolated branch are really the elementary excitations in your theory. Okay, and if you do this for the spin 1 Heisenberg model, you basically get these objects with a precision like 10 to the minus 12. Okay, so you basically know these energies, you know this Haldane gap using this method with an incredible precision. There's no other method by which you would be able to calculate these kind of things. Okay, so the really exciting thing is actually also is now when you have non-trivial excitations, when you have things like spinels. Okay, when you have things like topological defects in one dimensions. And this happens typically when you have symmetry breaking. Okay, if you have a ground state that is not unique, you have kind of a symmetry broken ground state, then the elementary excitations will typically be kind of objects, domain walls that will interpolate between the two ground states. Okay, but this can also easily be done. Basically what you do as an ansatz, you take this ansatz as an MPS, and then here you have something like this B tensor, and here you put somehow, so here you put basically the objects of one ground state, but once you have one ground state, you automatically also know the other ground state, because you just have to act with your symmetry operator that is broken, so this will give you the other one. So basically this is acting with some string of operators on this kind of thing, so you can just project it like this. And it turns out that indeed spinons and all these objects can exactly be understood like that. So these are basically the domain wall excitations, and these are very important, of course, in understanding the spectra of things. So, so I think we will have a short break here, and we will continue after that with trying to understand now the classification of phases. Okay, what happens now if you have symmetries, if you have kind of topological order? How can you deal with this in terms of matrix product states? Thanks. A question, yes? Sure. So there's no reason why these things only work for translation invariant systems. There's no, but of course then you can only do it for a finite system. People are using these methods for seeing this, yes. For the quantum. But of course, this is one-dimensional systems here, no? And two dimensions, all these things are a bit more challenging, but of course we are working on this. Is starting to work. Yes? Yes, this gives you basically the low-lying excitations. And, but of course, states in the middle of the spectrum, they typically, if you certainly have, if you don't have an MBL system or something, they will always have an entropy that is extensive. Okay, this is basically the whole kind of ETH. This follows from this eigenvalue thermalization hypothesis. So eigenstates in the middle of the spectrum have an entropy that is kind of satisfies a volume law, and therefore there's no hope whatsoever to represent them in terms of matrix product states. So this is about the elementary excitations. Okay, this is basically how can you actually access things in the middle of the spectrum by now obtaining or constructing an effective theory for these excitations. That's the way people do condensed matter physics typically, you know. So they find the ground state, then they find basically what are the elementary excitations on that ground state, and let's now construct a field theory for the many body physics of these excitations. And that step can of course be done. So we can start doing many body physics with these elementary excitations now. Okay, thanks. Okay, so let's continue now with a bit of theory about matrix product states. So one of the really cool features of these matrix product states is that it actually allows you to classify or to understand topological phases of matter. Okay, so these tensor networks are actually really made for that. They are kind of, it's clear this is the right language if you want to really capture somehow the way of understanding different phases of matter. So what is this whole idea of different phases of matter? Well, in some sense, in one dimension, what we have seen yesterday is that basically the manifold of all possible ground state of gapped systems is parameterized by matrix product states. Okay, so if you want to claim that two states are in a different phase, basically tells you want to make the claim that there's no adiabatic path such that at every time kind of remain in somehow the set of matrix product states that connects two states with each other. That at some point you have to go through some kind of a phase transition, and what this phase transition means in terms of matrix product states, it actually means that you break this injectivity condition. This condition that actually this transfer matrix had a unique eigenvector. Okay, so you know, so the eigenvalue, so the correlation length in your system was related to the gap in the eigenvalues of your transfer matrix. And if somehow the eigenvector or the eigenvalues are not unique anymore, you get an infinite correlation length, okay, because the gap closes. And that's equivalent to basically, so classifying different phases of matter is basically asking the question, is there kind of a smooth path between two matrix product states that, such that I never kind of hope to go through a phase transition. Okay, so unfortunately, actually, it turns out that for spin systems, there's nothing interesting. Okay, so if you kind of have spin systems and you don't have any additional restrictions, you can actually easily prove that you can go from any matrix product state to any matrix product states without ever having a gap. Which actually means that in the case of spin systems in 1D, there is only one phase of matter, and that's the completely trivial phase. Okay, because any matrix product state can be adiabatically kind of turned into another matrix product state by some kind of adiabatic evolution. That's not anymore true if you actually look at the case of fermions. Okay, I have not talked about matrix product states for fermions. I'm not so sure that I will have time to do this, but actually there's a student here from Caltech that has written papers on that, so if you want to have questions, you have to go to, what's your name again? Alex. So talk to Alex if you want to know, but in the case of fermionic matrix product states, you can actually deal this. It turns out that this is not true anymore. Your manifold basically splits into two disconnected parts, and there's no way anymore of going from one part to the other part. And these two disconnected parts are actually labeled by just the normal kind of normal phase of matter that have nothing special, and actually the Majorana chain of Kitaev. And it turns out that there's all this Majorana chain or this Kitaev chain has a very, very simple representation in terms of matrix product states. And the reason that you get actually non-trivial physics for fermions is that there's an extra symmetry. If you have, as opposed to just spins, if you have fermions, there's a superselection rule, namely that you have a Z2 symmetry. You cannot make superpositions of states with even an odd particle number. So if you have a wave function, the wave function must be a superposition of states with either all even parity or all odd parity, but nothing in between. And that actually, this extra Z2 symmetry makes sure that actually there is some non-trivial kind of classification, and there's actually two different phases. Okay, so this suggests actually that in the case of spin systems, there might also be some non-trivial phases of matter if you impose some extra symmetries. Okay, so, and indeed this is well known, and these are exactly the property, these are kind of these very famous SPT phases, symmetry protected topological phases. So what it tells you is that there is actually, I can give you several kind of matrix product states or different states that actually there is an adiabatic path between them if you don't impose any symmetries. But if you say that all these paths in between these two states must obey a certain symmetry, so they cannot break the symmetry, then certainly there's an obstruction. Because of course there's much less paths that you can do. And indeed it turns out that if you impose a symmetry, you say, look, I want to kind of look at paths between these two states, but I'm not allowed to break a symmetry, then certainly you have non-trivial phases of matter. And of course, the most famous phase of matter of that kind, or kind of version of or state that has such a property is the AKLT state. It's actually the one that is the state that is in the Haldane phase. Okay, and this is one of the reasons, of course, that he got the Nobel Prize, is that Haldane had understood already very early on that there's something topological going on with this AKLT state. Namely, if you have like this is spin 1 Heisenberg model, that actually there is something non-trivial. And what is the consequence of having such a non-trivial topological phase is that this has a consequence on the edge modes, on the entanglement spectrum. So this actually will mean that these eigenvalues of this reduced density matrix are always degenerate. Okay, so there's some kind of an extra symmetry that emerges. And I would like to explain basically how you can understand this in terms of these matrix product states, because it's actually very, very simple, and I think it's really beautiful how this works out so nicely. Okay, so how do we do this? So we need something that is called the Fundamental Theorem of Matrix Product States. So why did we call it like that? Well, it turns out that everything we have ever proven of value in MPS and matrix product states always follows from that thing. So that's why we call it the Fundamental Theorem of MPS. And I already kind of alluded to that in the first lecture. What it tells you is that psi of A is equal to psi of B if and only if. So I'm assuming now a translation invariant system. Okay, just for simplicity, that all the tensors are equal. And actually, by this I mean that independent of the length of the chain, so I take a chain with periodic boundary conditions, and independent of the length of the chain, these two things are equal to each other, then it turns out that there exists a phi and an x, such that it's e to the I phi x bi x minus 1. Okay, because the proof is actually extremely elementary, but kind of, at first it looks actually not easy to prove this. It looks like, how do you start proving something like that? So this arrow is completely trivial. If A is related to B by a gauge transform, then of course these two things have to be equal, but that's completely trivial. But that arrow is the non-trivial arrow. That if I kind of have two MPSs that are equal, that implies that this is true. So how do you prove this? I have to look at my notes because it's a long time that I did this, but it's just you prove it by Cauchy-Schwarz actually. It's a very simple application of Cauchy-Schwarz. So, so what do? Let's assume that I have this A and I have this row left. A bar is equal to row left. So this is basically the left reduced density matrix. Let's also assume that that B bar is equal to the identity. Okay, this is really, I put somehow the B in column. I can always do this, no? We have seen that we can put kind of these tensors into canonical form. And saying that psi of A is equal to psi of B, this basically means that if I would take the mixed transfer matrix, I put an A here and a B bar there, then the leading eigenvalue of that matrix with respect to left to right must have a modulus equal to 1. If it would be smaller than 1, then the overlap between these two MPSs would kind of decay exponentially with the system size. But if these are kind of equal to each other, then of course the leading eigenvalue of this has to be 1. Okay, so this means that I can put, there exists something like an x, such that this is e to the I phi times x. And this will certainly be the leading eigenvalue. Okay, let's put these things together. So I'm just assuming that this is true. Let's now use Cauchy-Schwarz in a non-trivial way. Okay, let's take this MPS A. Let's multiply with square root of rho. Another square root of rho. Let's put this x bar here. Let's put the B bar here. And the x here. Okay, this is just a contraction. Okay, this is just somehow an inner product. I interpret this now as an inner product of this vector with this vector. Okay, so that means I can use Cauchy-Schwarz. So this has to be smaller. So the absolute value of that thing squared has to be smaller than that kind of thing. So this means square root of rho A x bar A bar square root of rho. So this is the inner product of this with itself times the inner product of this with itself, so times square root of rho, x bar, b bar. Okay, so this is just Cauchy-Schwarz. No? This is like even something that you saw in high school. But now we make use of these properties. So I know that this square root of rho is the leading eigenvector of A, so I can basically erase these kind of guys. Okay, because this is an eigenvector of that object with eigenvalue 1. B bar, I had the property that is also the identity. A x b bar is also equal to x. So you see that basically all these objects are equal to each other. So that means that this is an equality. And that means that these two vectors with the A here that means that this thing must be proportional to this thing. And that means that we have proven what we want. Okay, because it is like square root of rho ax is equal to square root of rho x bar b bar. And that's exactly equal to this kind of statement. So and this is basically the theorem that will kind of allow you now to classify phases of matter and do all the kind of... Also, actually, this is the basic building block to do everything in 2 dimensions and higher dimensions. Yes?
What is ax b bar equal to x?
Sorry, what is the question?
We constructed... could you repeat this?
So I brought this A and the B into canonical form such that these properties are true. And that's the only, these 3 properties are the ones I need.
Okay, the ax b bar equals to x. Could you explain the upper one?
So if these 2 MPSs are equal to each other, that means that their overlap must be 1 up to a phase. And that's only possible if this transfer matrix, when you have an A and a B on the top, because that's exactly what you get and you calculate the overlap between them, that this transfer matrix must have an eigenvalue with modulus 1. And this x would be the eigenvector corresponding to that kind of guy. So that means that this x is exactly the one that interpolates, or is the gauge transform that will kind of map A to B. Yeah, but I'm talking about systems in a thermodynamic limit here. But of course, so yeah, but because of course this, because I said this is, so I want a uniform MPS, and this thing has to be true independent of the system size. There's actually enough to say, of course, you can immediately go to the thermodynamic limit, and that's also okay. Okay, so let's actually apply this now to a state that has that satisfies a symmetry. For example, of course, the most famous SPT phases are kind of the ones that are invariant under reversal. Okay, so what would be, for example, time reversal? So I have an MPS, okay, with all A's, and so further. And if this state is invariant under time reversal, this means that this guy has to be equal to, I just take the conjugate. So I'm assuming here that in time reversal that, okay, that in the case of Wigner, that somehow the unitary I have to apply on my spins is the identity. But anyway, so this is we of course do this for the most general anti-unitary symmetries. Although maybe it's the time reversal is already a bit complicated, but nevertheless, let's do it for time reversal. And just believe me that it's okay to just take the conjugate of your tensors. Okay, I have an A, and the conjugate, somehow the time reversed version of my kind of ground state is the one where you put all the bars. And if your Hamiltonian has time reversal symmetry, that means that the ground state, so that means if you kind of take the conjugate of your Hamiltonian, it remains invariant, then the ground state must have this property. So that means this is A, this is B. So that means that there must exist a phi and an x such that AI is equal to the e to the I phi x times AI bar times x minus 1. So there must exist such an object. Okay, this follows from this fundamental theorem. So let's do it twice. Okay, let's now take the conjugate. This is a minus, a bar, a bar, a bar. So this is AI. So that means, no wait, what did I do? Actually, I wanted this. I'm sorry. So A bar I is e to the I phi x AI x minus 1. Okay, let's take the bar again. Okay, so this means AI is equal to e to the I phi, e to the minus I phi x bar AI bar x bar minus 1. So this is elements-wise conjugation. But this A bar I can replace it by this. So this is e to the I phi x AI x minus 1. This phase e to the I phi cancels this one. So now I see that AI is x bar x, AI x minus 1, x bar minus 1. Okay, and now the uniqueness of the fixed point of your MPS, okay, this notion of injectivity that we did not really kind of touch upon, but it's actually easy to, this the equivalent to saying actually this eigenvector, this transfer matrix has a unique eigenvalue, says that what it means is basically I can bring this to the right hand side, so x bar x is equal to this. So what it tells you is that the only thing that commutes, the only operator that commutes with all your matrices AI must be proportional to the identity. That is actually follows from this Frobenius theorem and all these kind of things. This is actually easy to prove. That means that x bar x has to be proportional to the identity. This just follows from this. Okay, but x bar x proportional to the identity, and okay, just up to a phase. Let's take, for example, the trace of that object. If I take the trace of an object x bar x, I'm guaranteed that this trace is real. Okay, you can easily see that. That's actually a matrix and a conjugate. You kind of take the trace of the product of these two. This has to be a real value. So that means that this phase can only be plus and minus 1. And now we are basically done. Now we have an index that cannot be continuously be deformed into each other. If I give you two MPSs, and one MPS has the property that this sign, that if I under time reversal this sign is plus 1, and another MPS has the property that under time reversal this sign is a minus 1, obviously there will be no continuous path interpolating between them, because I have an index that cannot jump continuously from plus 1 to minus 1. Okay, and so that's, and the example, of course, the beautiful example that satisfies this is actually the AKLT chain that we kind of talked about before. So what is the AKLT chain? In the AKLT chain, the matrices AI are nothing more than the Pauli matrices. Okay, so you have kind of three, you have sigma x, sigma y, sigma z. These are the Pauli matrices. So let's try to understand what actually this x is and what this phi is. Okay, so under time reversal, so if we look at somehow sigma x bar, this is nothing more than sigma x. Okay, sigma y bar is of course minus sigma y, and sigma z bar is equal to sigma z. So what is the transformation that does, what is the gauge? So we know that now there must exist a phase phi and an x for which these kind of things are connected to each other. So what is this phase? Well, it's very easy to see that actually the phase phi has to be minus 1 and x is basically sigma y. Okay, so this is indeed, you see that this is equal to minus sigma y, sigma x, sigma y. This is equal to minus sigma y, sigma y, sigma y. And this is equal to minus sigma y, sigma z, sigma y. That means that the gauge transform x, so that means that e to the I phi is equal to minus 1, and the x is basically sigma y. Take sigma y times its elements-wise conjugate, and you get minus 1. So that means that indeed this AKLT chain is kind of topologically protected under time reversal. If you kind of only allow for paths and all these paths have to kind of preserve time reversal symmetry, you will not be able to connect this to the trivial state. And of course, there's hidden here, there's something more, no? So the EQLT state also has to satisfy, it has to preserve basically the translation invariance. Okay, this is an implicit assumption that I made here. Okay, if you break translation invariance completely and you start blocking sides and so further, you will be able to actually map the EQLT state to a trivial state. But of course, implicitly here we are assuming that I have a translation invariant system and I don't break this translation invariance with respect to one side. You can just do this in a much more general way, actually. Okay, now you can do this for any symmetry. So this time reversal is a simple symmetry, but you can actually do this. So the same EQLT state has many other symmetries. Okay, but let's do it in general. I have an A, and I act with a U. Let's now just look at on-site symmetries. I act with an on-site symmetry on my MPS, and it remains. Somehow there's a symmetry that commutes with my Hamiltonian. I have a unique ground state. Well, okay, so if I act with this unitary on my ground state, it has to remain the ground state invariant. So fundamental theorem tells you this has to be equal to e to the I phi, function of g, times x g a x g minus 1. So there must exist, so for every group element g, there must exist a virtual kind of representation, xg, that kind of satisfies this. But now there's something very interesting going on, in the sense that there's no particular reason why x of g has to be a representation of that group. What you see is that if I kind of multiply ug and I have uh here, well, obviously this will kind of give me the group element gh, and indeed I will get xg times xh here. But you also get the inverses. So what it basically tells you is that this xg does not have to be a representation of the same group. Only xg tensor. So typically if you work in the right gauge, this is nothing more than basically xg dagger. It's like the conjugate. Okay, what it tells you is that xg times xg bar has to be a representation of the same group. Okay, because you act with one element here, but you always get two elements on the virtual level. Okay, so it means that this has to form a representation of the same group. And for people that are familiar with SU2 and all these kind of things, you immediately start seeing the light, I guess, no? So in the EQLT chain, I have a spin 1 system. So that means that actually the group, the symmetry group is O3. Not SU2, because of course, if I have a spin 1, I have an integer representation of my group SU2, and this is actually the group O3. But actually this is given by the Pauli matrices, and on the virtual level, we know that exactly this representation of O3, this will give rise to an SU2 representation. And you all know that SU2 and O3 are different groups. Okay, SO3 and SU2 are really different groups. They have the same Lie algebra and so further, but they have like for every kind of element in SO3, there's actually two different elements that correspond to it in SU2. There's kind of a double, I have a cover, so the SU2 is like the cover group of SO3. And indeed, this is exactly what is going on. What is going on is that somehow this x of g only has to be a representation of the group g up to a face. So what it means, and this is exactly what is going on with SU2 now. So if you multiply two elements of SU2, this gives rise to kind of another element, but it's not it doesn't form a representation of SO3. It only forms a representation of SO3 up to a sign, namely a minus sign. And in general, somehow you can play this game now, and it's what you want is, in some sense. So what it amounts to is the fact that you want to find basically what are all the possible symmetries. So how can I kind of represent the symmetries on the entanglement spectrum? Because this is something very important. This x of g's will of course be symmetries also of the entanglement spectrum. Okay, so if somehow you look at this reduced density matrix that we calculated before, and I have a certain global symmetry, well, this density matrix is invariant under that kind of symmetry group. And that actually immediately also implies that if I have some non-trivial symmetries, if this is kind of a non-abelian kind of symmetry, then my degenerate non-abelian symmetry, somehow this will immediately imply that my entanglement spectrum is degenerate. And this degeneracy of the entanglement spectrum will immediately also have an effect on the edge modes, that you will have some kind of non-trivial symmetry. And that's exactly what is going on somehow here in the case of the AKLT model. But in more general, what you're interested in is basically I give a certain group. I have a certain group. What are all the possible projective representations of that group? And a projective representation of a group is like I have a normal representation has the property UG times UH is equal to UGH. Okay, so you have a group, and if I kind of multiply two elements, well, this is the definition of a representation. It's a matrix representation of a group. What you see is because I have a XG tends to XG bar, the only requirement that I have here is that XG times XH is equal to XG times H up to a phase e to the I omega g h. And this phase can depend really both on g and h. And now there's actually some very nice just linear algebra that you can start doing. And you can start asking, what are all the possible omegas that I can put here? So given a certain group, how many different projective representations are there for a given group? It turns out that this is classified by something that's called a cohomology, okay, group cohomology of kind of your group versus U1. And this all looks maybe kind of very complicated, but it's actually very simple. This is to given a certain group, to calculate basically all the possible ways in which somehow these phases can occur. It's just a simple linear algebra problem. Okay, I can just put it in my computer, I give the group, and it will spit out, look, these are the possible ways in which this can be realized. And this is actually what is then giving you this kind of group theory. So basically this thing will tell you, this is always of the form, a typical thing is Z2 times Z2 times Z3 maybe, and so further. So this is actually, this group is always abelian. It's a product of cyclic groups. And what it tells you is that actually for every element in this group will correspond to a different realization. And importantly, there is no way that you can adiabatically continue one of these solutions to another of these solutions. So for example, if this is, so in the case of this AKLT model, and you take basically O3 or SO3, then basically this will tell you is if you put SO3 here versus U1, what you will get here is Z2. And what are the two solutions? Well, of course, it's just the integer representation, so just the representation of O3 that are faithful, and actually the projective representation, this is exactly Z2, SU2. Okay, but you can easily do that for any group, actually. And how do you do this? Why is this nothing more than a simple linear algebra to find all these kind of projective representations? It's really that there is some kind of a notion of, or a condition of associativity that you have to impose. Okay, so if xg times xh is equal to xgh e to the I omega gh, well, it's clear that if I kind of take three group elements, g1, g2, g3, there's basically two possible ways of, because the product of matrices is associative, there's two possible ways of doing that. I can first time take these together and then multiply with this, or I can first take these together and multiply with this. And of course they have to give exactly the same result. And you can immediately see that this implies that omega g1, g2 times g3 plus omega g2, g3 has to be equal to omega g1, g2 plus omega g1, g2, g3. And that's actually a linear condition up to 2 pi. So you have to see this is actually an equation that only has to hold modulo 2 pi. It's exactly the fact that it only has to hold modulo 2 pi that actually there can be non-trivial solutions. So what you have to do to solve this is a set of linear equations. So for example, if I have a group, okay, let's take the group Z2 times Z2. This is the simplest actually group that has a non-trivial second cohomology group. So it really is Z2 times Z2, the symmetries of, what is this, the symmetries of a square? No. Square has more symmetries than that. Anyway, Z2 times Z2. So that means that for every, so the group has 4 elements. Okay, Z2 times Z2 has a group with 4 elements. So what this equation tells you is that I have 4 to the 3 equations. This is 64 equations for a number of unknowns that is 16. Okay, so I have 16 unknowns. Because for every element G1, G2, G3, this equation has to satisfy. So it has to be satisfied. Okay, so this is just a linear problem. I have a big matrix A times omega has to be equal to 0 modulo 2 pi. And actually, this can directly be solved using something that is called, I don't know how many people are familiar with this, but this is actually something very powerful, the Schmidt normal form. So it's nothing to do with the Schmidt normal form. This is the Schmidt normal form, which tells you that if I have a matrix with integers, okay, this is a matrix with integers, and actually this matrix, you immediately see this is a linear equation, no? So this is there's only integers in this matrix. It tells you times omega is that every matrix A can be written down as a U times a sigma times a V. So it looks very much like the Schmidt decomposition, the singular value decomposition, but it has nothing to do with it. What it tells you is that every matrix basically has a unique decomposition in terms of 3 objects. Namely, so this is all integers, no? So I only have integers, and all these matrices only contain integers, but I'm guaranteed that this determinant of U is equal to plus minus 1, and the determinant of V is plus minus 1. Okay, so because you're working over somehow the integers, of course you cannot work with unitaries and all this, but you can work with matrices U and V that are basically, I forgot how this is called in mathematics, but anyway, the determinants of them are equal to 1. Okay, so they're basically matrices with integers with determinant 1. That means that their inverses are also matrices with only integers. Okay, because you take a matrix and you take the inverse, well, you have to take these minors and divide them by the determinant. But if the determinant is plus or minus 1, well, then obviously this is also a matrix of integers. And this is basically, so this U and this V are not unique at all, but this sigma is unique. This is called the Schmidt normal form. So what you do is basically look at these equations, and this A is completely determined by the group multiplication rules. Calculate the Schmidt normal form of that kind of matrix A. And this sigma that will come out will typically look like a 2, a 2, a 1, 1, and then all zeros. That's a typical, it's a diagonal matrix with decreasing elements on the diagonal, and actually every next element has to divide the previous one. So for example, you could have, well, okay, let's just take 2, 2, and all kind of ones. But this is something they can just put in MATLAB or Mathematica. They have this, the Schmidt normal form. You calculate this. And if this would come out of the Schmidt normal form, I immediately know that H2 of my group U1 is equal to Z2 times Z2. Why is this? Basically because these matrices V and U are basically determinant 1, I can't forget about them. And this equation becomes equivalent to sigma times omega is equal to 0. Well, actually, so let's of course, if I redefine omega by multiplying it by 2 pi, this is actually up to the integers now. So this is really, I want this to be 0 in somehow up to the integers, so that because I want to work with integers, I don't want to work with pi's. So I basically want that A times omega is an integer. And you see that if sigma times omega has to be 0 modulo the integers, and I have like a 2 standing here, and a 2, and then all 1s, and then all zeros, then there's indeed a non-trivial solution here, because I can put a 1/2 here, or I could put 1/2 here, but all the rest has to basically be 0. And that means that there's non-trivial. I can put 1/2 here and a 0 here, or a 0 here and 1/2 here, or a 1/2 here and 1/2 here. And that's exactly the 4 possibilities. I can put 0, 0, 1/2, 0, 0, 1/2, or 1/2, 1/2. These are the 4 possibilities that I get. So this is how you can actually understand this kind of fact that indeed these are topological non-trivial. You cannot connect them to each other. And actually the zeros that you get here, these are so-called boundaries, co-boundaries. So for the people that know more about cohomology theory, well, you have some kind of trivial co-boundaries. Well, these co-boundaries correspond to basically the null vectors of that matrix A. And these, of course, you can continuously deform them, but it's clear that these numbers you cannot deform. Okay, because they are kind of completely specified by this. And this is how kind of things work. Okay, so this is how, given a certain phase, now you can understand what cohomology is. Cohomology is actually, it's all very simple linear algebra. I give you some kind of a group. I kind of give you a Hamiltonian. You calculate the Smith normal form. You find basically these matrices. You look at this. You kind of, this information about actually what is the omega itself is completely contained in the V's. And once you get one of these V's, you can actually write down a matrix product state that will have exactly these symmetries. Okay, that's the nice thing actually, that once you solve this and you found a non-trivial omega, then I can immediately define a matrix product state AI that actually has this kind of symmetry. Because you see, the property that I had is that xg1 times xg2 is equal to xg1 times g2 times e to the I omega g1 g2. That was basically the defining property of a projective representation. So what this mid-normal form gives me is a solution of this omega. It tells you, look, this omega, if I choose this omega, this will give me a non-trivial solution. But now if you look at this equation carefully and you write it down, and maybe I leave this as an exercise because there's not much time, you can actually see that I can choose this xg1s just as a function of omega, in such a way that this equation is completely equivalent to the co-cycle equation. Okay, so I can actually make x define it as a function of these omegas, such that this equation is really equivalent to that one, and of course it's automatically satisfied. And that means that I can, for every solution of this Smith normal form, I can actually construct an MPS that has these properties. And of course, they cannot theoretically not be connected to each other because somehow there's no way in which these indices can suddenly jump. Okay, and this is basically the story of SPT phases in 1D. So time reversal, for example, is another case of this. So it turns out that in time reversal, there's a little bit of a more subtle kind of game you have to play. Okay, so this is also kind of fits completely in the context of these co-cycles, but you have to kind of, instead of this, you have to add somehow -1 to some parity of G1. Okay, this is actually something that's called a twisted kind of co-cycle. Actually, no, this is always, I have to think about this. This is, well, indeed, if G1 includes a time reversal, then I have to put a -1. If G1, the element G1, of course you can have time reversal plus other symmetries. So if it's time reversal, I have to put a -1. If it's reflection, I also have to put a -1. If it's time reversal and reflection, I have to put a +1. And so this, but this is always, all these kind of things fit perfectly well in this whole formalism of cohomology theory. Okay, and it's just, it just depends on how this thing is defined. So to define basically this second cohomology group, you have to specify basically the action. How is this co-cycle defined? What kind of action can I have on these extra elements such that kind of it goes? But this is all kind of still perfectly well kind of defined using this MPS. And the great thing is that once you have this, once you find a solution, I can immediately write down an MPS that satisfies this. And these MPSs are actually all MPSs that would have 0 correlation length. So these would kind of be MPSs that they have no correlation length, nevertheless they are topological, and they have some very non-trivial information in the sense that there's no way to adiabatically continue them into each other if you want to preserve the symmetry. And in the case, if you would do this, for example, for the AKLT model, okay, you start with the AKLT, you calculate what is this omega, and then you would have to find what are these matrices. Oh, sorry, I jumped too far. Okay, I skipped something. This equation is equivalent. You can make this equation equivalent to the co-cycle equation. You find the xg's. Okay, but now I still have to find the equation that AI times my unitary acting on I prime has to be equal to xg AI xg -1. So this defines basically the gauge transforms. But now I still have to find what are my tensors AI that satisfy this. But then you write this thing down, which is this equation, and then you look at this we say this xg -1, I put it to the right here, xg -1 is equal to xg to 1, and then this equation also turns out to be completely equivalent to the co-cycle condition. Okay, so it's just everything kind of is given you for free. Okay, so that means that the AIs at the end are just, the elements of AI are completely determined by somehow this co-cycle, and these are of course these MPSs. And if you do this for the Haldane phase, you would get actually something that is called the cluster state. Okay, this is actually the cluster state is exactly indeed the kind of state that would be the zero correlation length kind of element in that class, in that SPT phase. So for every one of these SPT phases, there's actually a fiducial state that has no features besides the topological information. Okay, so you can of course now start playing this game with fermions, and with fermions it turns out to be pretty analog. It's a little bit more interesting because you have the super selection rule, and you have to work with graded vector spaces and so, but at the end, it's still actually exactly the same framework. So it's still the second cohomology group that comes out of it. But if you want to know more about this, you should talk to Alex. I think, well, it's probably time, so I wanted to stop here. So I also, there's still, but no, but let's keep the rest for the next lecture. So the next lecture will really about the two-dimensional versions of this. Okay, so how can we lift this whole framework now to two dimensions? And what you will see is that, like for topological order, or at least the simplest versions of SPT phases and 2D, this whole scheme will kind of carry exactly through. Instead of 2 code cycles, you will have 3 code cycles that you have to solve. Okay, this is a little bit more complicated, but it's very similar. And given the 3 code cycles, you will be able to find basically some objects that satisfy this thing, and this will be matrix product operators. So what you will get is some non-trivial symmetries. This, instead of this XGs will now be represented themselves by matrix product operators that form a representation of that non-trivial code cycle. And then you will be able to construct PEPS tensors that have exactly this property, also again in terms of the solution of these code cycles. And this will be basically all the quantum, so this will give rise to, on the one hand, the SPT phases, the non-trivial SPT phases in 3D and 2D, but also actually all the quantum doubles and the twisted quantum doubles. Okay, this will be basically some gauge theories that already have true topological order, and the toric code state is one very particular state in that. But there's much richer kind of guys. You have the double semyon, you have all these things are there. And then it turns out that you can actually even generalize this kind of, you don't have to impose that actually these matrix product states form a group. It's enough that they form an algebra, and this then will give rise to something that is more rich and will kind of be somehow through all the topological phases that you can have in 2D will be able, or at least the non-chiral ones will be able to represent them like that. And they will have an extremely interesting connection with conformal field theory. So that's the plan for the next lecture. Thanks.